Let's introduce our speaker again. The next speaker is Professor Volodymyr Bavula from University of Sheffield. And his talk is on data locally nilpotent algebras, their ideal structure and simplicity criteria.
Okay. So can you see now, right?
No.
No. Okay.
You're not sharing.
Not sharing, right.
Yeah.
Share camera, Dropbox, Microsoft.
Oh.
Now it's okay, right?
Almost.
Yeah?
Oh, it's okay.
It's okay. Okay. Sorry about that.
Okay.
Okay, so my talk is about a new class of algebras, and these algebras are called locally nilpotent algebras. And I will talk about ideal structure and simplicity criteria. And these algebras are generalization of rings of differential operators. And so the structure of my talk, so we consider algebras of differential operators and their simplicity criteria. Then we introduce locally nilpotent delta locally nilpotent algebras. Consider examples and the ideal structures. And this, I'm talking about these two works. So let me recall the algebras of differential operators, because this will be a generalization of the rings of differential operators and the results. So in my talk, module means left module, and field is arbitrary, of arbitrary characteristic. I is a commutative algebra, and we denote there by left module of k derivations. So let me recall the rings of differential operators. So we start with a commutative ring R, and the rings of differential operators is defined as a union of vector spaces. They are defined inductively, starting with minus component, which is 0. Then 0 component is simply the endomorphism ring R, which of course can be identified with ring R. And then inductively for all R, I, which is larger than 0, it's given by this rule. Just look yourself. I will give you 10 seconds. So this is a definition of the rings of differential operators. Very difficult to compute in general. And it's clear by the definition that we have an increasing order filtration. So this is an increasing vector spaces, just follows from the definition. And also it follows from the definition that this is actually filtration of an algebra. So it means when we multiply di and dj, we've got di plus j. This is straightforward from the definition. So now our algebra dr contains a very important subalgebra, which is denoted by delta. And this algebra is denoted by the rings and all the derivations. And this algebra is called the derivation algebra. So when we look at the regular case, no regular, it means smooth if you are algebraically closed field, so almost identical. So there are no singularities if you want to. So we start with the regular, affine domain of crude dimension larger than 1 and characteristic 0. Then in geometric terms, R is a coordinate ring of a smooth irreducible affine algebraic variety of dimension n. Then when we look at the module of derivation, this is a finitely generated projective module of rank n, which is a dimension, crude dimension of our ring R. And very important fact that in this case, our algebra coincides with derivation algebra. So it means rings of differential operators is generated by the derivatives and elements of the ring, which is not the case in general, and that is why it's difficult to compute in general, even in examples. And the most important property are the algebra is simple and also Noetherian domain. And the Gelfand-Kirillov dimension is twice larger than the algebra. Okay, so when we look at this, when we look at the singular case, none of the properties simple or Noetherian doesn't hold. It could be left Noetherian and not right Noetherian. All possible combinations are possible. So this was first shown by papers of Gelfand, Bernstein, Gelfand, where they consider conic and they produce, using very non-trivial homological, actually, the result to produce that algebra is, I remember it was simple, but not Noetherian. Okay, so these rings introduce the general algebraic definition of rings introduced presumably by Grothendieck in 50s, and the simplicity in regular case of differential operators, rings of differential operators, also proved by him. And from that moment, it was open question. But there are many examples when the algebra is singular, but the rings of differential operators is simple. And it was a long question, give a criteria when the rings of differential operators is simple. And several years ago, I give the criteria, and the answer is surprisingly very simple. It's really, so this is the next. So in theorem 1 and 3 below, I will give a simplicity criteria for algebra of differential operators, where A is a domain of essentially finite type of a perfect field. So essentially finite type, it means we have a fine algebra and localize it. So invert arbitrary elements, no, which are localizable. No, if you domain that any elements non-zero are localizable. And perfect field, important restriction. For example, every field in characteristic 0 are perfect, but in characteristic P this is not the case. And so in theorem 1, we give criteria for this situation. And in theorem 0,3, we give in general for commutative algebra of arbitrary field, there is no restriction. Okay, and the aim of my talk is to generalize this result, which I'm going to explain, to more general class of algebras, so-called the delta locally nilpotent algebras, but I will generalize not for all algebras, but for certain class, because it's huge class of algebras. And these algebras includes the rings of differential operators, so we will get the result I'm going to explain, and also algebras of differential operators that contain the algebra A. This is also a huge class and important class. And this class contains many exotic algebras, non-Noetherian, non-finitely generated, and so on and so on. So the answer, so this is a simplicity criterion for rings of differential operators when our algebra is commutative domain, essentially finite type of a perfect field. Okay, so we have such an algebra, which is a localization of finitely generated algebra. Hence, we have the generators, finitely many relations. So when we choose the relation, we have the Jacobi matrix, simply the gradients of all the generators. So now look at the minors of possible. Look at the submatrices of maximal possible rank. Consider that they are determinants. Determinants will be the elements in A, and look at the ideal generated by these determinants, and this by definition will be Jacobian ideal. And this is precisely the ideal that solutions to the equations that belongs to this ideal determine the singularity if and only if in this situation. In general, this is not the case, but when you have essentially finite type, this ideal, which is called the Jacobian ideal, determines singularity. So now the answer. So the following statements are equivalent. So we have a differential operators, and this algebra is simple. if and only if. So we take this Jacobian ideal, so this is ideal in the commutative algebra A. So when we raise it to i's power, we will get small ideal in algebra A. So now we produce the ideal in the rings of differential operators, and this must be the whole ring, and that's it. So it means that we have to effectively produce accountably many checks of the powers of the Jacobian ideal, whether these powers generate the whole thing, and that's it. So it means, or this can be translated using these minors I have just mentioned. So this is a precisely non-zero minors of maximal rank in the Jacobi matrix, and similar. So there's finitely many of them. So this condition means that these minors are non-zero, right? And we have to check with these minors, not necessarily with ideals, especially if there are plenty of zero minors. Okay, and let us look at this classical result, that when we have a smooth algebra, then this algebra is differential operators is simple. Simply, when we have a smooth algebra, there is no singularities. Algebraically, it means the ideal, Jacobian ideal, is the whole algebra. And then when we put here the algebra A, it's clear we have the equality for all i's. So this is a short proof of this classical results. And theorem just mentioned reveals the reason why some singular algebras and their rings of differential operators are simple. And you see, it's possible that for some small i's you will get the equality, but for higher i's you don't have it. But suppose we don't have this equality, to find this I, it's a kind of, it would be interesting if you to say something about this number when we don't have this equality. Okay, so now, for example, in this situation for the cusp, so this is a singular algebra, but the rings of differential operators is simple. So now when we look at the commutative situation, so we have a commutative domain of essentially finite type of a perfect field. So the same situation as in the previous situation. And the following statements are equivalent. So the algebra is simple. And what we do, so we have the Jacobian ideal, and we have a maximal ideal that contains the Jacobian ideal. When we look at the localization at this maximal ideal, then the answer is the simple algebra. So if you want to prove it using localization, you have to take the maximal ideals that contain the Jacobian and to prove that the localized algebra is simple, which is also a useful criteria in applications. So now look at this in general situations. This is a simplicity criteria of differential operators for arbitrary commutative algebra. Okay, so we have a commutative algebra, and we have an ideal of this algebra, and this ideal is called delta stable if it is stable ideal after when we apply any derivative, so we are inside the ideal. So this ideal, this condition is very restrictive condition. Then the theorem below is a simplicity criteria for arbitrary commutative algebra. And theorem also showed that every non-zero ideal meets the subalgebra, and this is an important property. And in a particular case, we have just considered when we have the algebra of domain of essentially finite type, it shows that that any ideals contains a power of the Jacobian ideal. So in some sense, this is a generalization of the previous result for commutative algebra. Okay, so we start with a commutative algebra of an arbitrary field, and we consider a non-zero ideal of the rings of differential operators. Then we intersect this ideal with a zero component of the differential operators, which is our ring R. And the statement is this is a non-zero ideal, which is stable with respect to all derivatives. And when we intersect it, when we take this ideal, which is ideal in R, generate the ideal of the ring and intersected with R, we've got the original I naught. In particular, every non-zero ideal intersects with, not trivially, with R. And the ring, or equivalently, if the ring is not simple, if there is a proper, they're stable ideal such that we have this intersection. So this could be kind of way to prove that the ring is not simple. And as I mentioned below, if field is a perfect and algebra is essential domain of essentially finite type, and when we take non-zero ideal of the rings of differential operators and take the intersection with the original ring, then it contains the power of the Jacobian ideal. Okay, so now we come to the delta locally nilpotent modules, and then we will define the delta locally nilpotent algebras. So we start with the K algebra and look at the A module and look at the set of endomorphisms. Simply, we have a module and set of endomorphisms, and look at the power of this set, which is by definition all the possible products. And now we introduce a module which is denoted NM, which is a union of vector spaces, which simply annihilators. So these vector spaces are simply annihilators of this set. So it means the set of all elements that annihilated all these elements, all this product. Now it's clear by definition that we have the ascending chain of submodules. And it follows from definition when we add by this set delta, it will drop this kind of filtered degree. This follows straight away from the definition. So, and this submodule N is called by definition delta locally nilpotent module. Delta locally nilpotent module because when we apply sufficiently many delta to any part, we will get zero, right? So this is, and if we have the equality, we simply call our module is delta locally nilpotent module. So suppose we have an endomorphism, and this is locally nilpotent map. If this is a union of kernels, is the whole module. So if M is a locally nilpotent A module, that every map is locally nilpotent. So that every map is delta is clear, but not vice versa. But we have a condition if and only if this lemma gives a condition if and only if. So suppose you have a finite set of commuting a homomorphism of a module, that the module M is locally nilpotent if and only if the maps in delta locally nilpotent. So this is a very important if you want to, no, this is a typical situation. We have a finite set of commuting element, and to check the local nilpotency, you have to check that the maps are locally nilpotent. But none of these conditions can be dropped, neither finiteness nor commutativity. Okay, so now we come to the main object of the talk, so-called delta locally nilpotent algebras. So suppose in addition, so we have an algebra, and this is a subalgebra of abstract algebra E, and we take the set of A derivations of this algebra. So before it was arbitrary set, but now we consider the set of derivations. And this is a set of A derivations. So it means this is a derivation, and since it's A derivation, it means it kills the elements of A. So now when we look at this intersection, so it means the elements that are killed by all deltas, this is the algebra of delta constant. And it's clear then we have this equality because our derivations are delta derivations. Then so now situation as above. So we consider this module, And this module actually is a subalgebra because we consider derivations. And hence we have, and moreover, this is a filtered algebra. And these elements define a Sandel filtration on this algebra. And obviously we have this inclusion. So hence this algebra is called delta locally nilpotent algebra. And this filtration is called the order filtration by definition. And we say that an element that belongs to this set has order I. And look at the examples. So there are plenty of examples. So for example, we have a commutative algebra. Instead of E, we take the K endomorphism algebra, which obviously contains A there. And when we take deltas, all the inner automorphisms of this algebra E, which is given by a bracket, and then consider this algebra and E inside E, this will be precisely the algebra of differential operators, right? So this is delta locally nilpotent algebra are direct generalization of algebra of differential operators. And moreover, this filtration, which is given, this is precisely the order filtration of the algebra of differential operators. And so what about the examples? So when we take the algebra of differential operators and take arbitrary algebra that contain the algebra A, then it will be delta locally nilpotent algebras. So if you take even polynomial ring of A is equal kx, take differential operator, suppose characteristic 0. It's a Y algebra, and take two elements, say A2, A3 of degree 2 and 3, two differential operators of degree 2 and 3, and add x here and produce the algebra which is generated by x. And this two differential operators of degree 2 and 3, you will see how difficult to deal with. Even to find the basis will be difficult. So it means this is a very tricky class of algebras. Okay, so Y algebra is obviously, because it's differential operators. Then when we look arbitrary nilpotent algebra, take its universal enveloping algebra and take inner derivation coming from M, then our algebra, it will be delta locally nilpotent. Similar story with solvable algebra. So we have a solvable Lie algebra. When we take its kind of nilpotent part, commutator, then we look at the delta similar as above, then the universal enveloping algebra, it will be delta nilpotent algebra. So let me look at kind of two more classes, and we will go to main results. So when we take arbitrary Poisson algebra, and we take its universal enveloping Poisson algebra, then it will be delta locally nilpotent algebra. Simply take the Hamiltonian vector fields. That's it. And most important class, so-called algebra of Poisson differential operators, introduced several years ago in one of my papers. And this algebra contains P, and this is a subalgebra of differential operators. And this is a tricky algebra. So this also explained why this class I've just mentioned, when we start with differential operators and take any algebra that contains P, for example, the algebra of Poisson differential operators, is an important algebra. Okay, so let me move to kind of, because I have only 2 minutes left. Right, so let me look for simplicity criteria. Simplicity criteria for subalgebra that contains A. So we have rings of differential operators, and this is the commutative domain of essentially finite type of a perfect field. And we have the differential operators. and we take any subalgebra of differential operators that contain A, for example, the Poisson differential operators. Now we have these intersections of your algebra with filtration, Ri. So this is our submodules, and take the left annihilator and right annihilator of these modules. Then this is a non-zero annihilators, and also we have these inclusions. And we have a simplicity criteria. For example, this gives the simplicity criteria for Poisson differential operators, but also for any algebra that contains R. So this algebra, the following statements are equivalent. So this algebra is simple, for example, the algebra of Poisson differential operators. When the original algebra is differential operators is simple because of this criteria. And for every I, product of this ideal generates the R. And similar other conditions, the variants of this. For example, our algebra is simple algebra, and this condition holds, and some other useful conditions. And also, suppose we want to look at kind of localizations. Well, there are several criterions like that, but unfortunately my time is up. So suppose we have the similar situation, but when we have a subalgebra that contains A, such that localization of this algebra gives you the localization of your differential operators with respect to multiplicative set, then all these ideals as above, but we simply choose an elements there. This is elements from S, and then the algebra is simple if and only if the original algebra is simple because of my criteria, and you have to check this condition. Then this particular element generate the whole ideal, right? The whole algebra. Okay, thank you very much, yeah, for your talk. Okay.
Thank you very much.